Okay, so here is our lecture video for section 6.5, operations with radical expressions. We're basically just expanding on what we did in section 6.4 with simplifying radicals and adding different operations. And by operations, I mean adding, subtracting, multiplying, and dividing. Some rules that are going to help us simplify here. We got some multiplying rules and some dividing rules. Is that when we are multiplying square roots, nth roots, cube roots, whatever we're multiplying, you can multiply the insides as long as the index is the same. So like for this example right here, these both have that invisible 2 for the square root. Since they both have an index of 2, we can just multiply the 8 and the 2 together to get 16. Same idea over here, they both have that index of 3. It's a cubed root there, so we can just multiply the 3 and the 9 together to get the cubed root of 27. And a little note down here, in order for a radical to be in simplest radical form, the radicand, what's underneath the square root, must contain no factors that are nth powers of an integer or polynomial. So basically you just have to simplify it to lowest terms and just double check that you're doing that. That's kind of all that note is saying. So let's try some examples here. Okay, example 1, simplify expressions with the product property. Basically, we're going to do the exact same thing that we did in section 6.4, but now we're just going to have something left over. We're not going to have complete perfect squares the whole time that just gives us a nice result at the end. It's going to have a little bit left over, which we've actually worked with a little bit before. So let's take a look at part A right here. We're just going to simplify this. It's just a square root. There's that invisible 2 right there as our index, so it's just a square root. So I'm going to think of a perfect square that divides evenly into 32, and right away my head jumps to 16 because 16 times 2 is 32. So I'm just going to rewrite this a little bit. I have 16 times 2, and that's kind of how I handle the numbers here. And then when dealing with the variables, since it's a square root, I want to think in groups of 2 or pairs. Well, 8 divided by 2 is 4, which means that I have 4 x squares, right? So then from here, I just have to simplify a little bit. Square root of 16, well, that's 4. We all know that. Square root of 2, on the other hand, not a nice number, right? That's an irrational number, so that's going to be what's left over. That's part of our leftovers here. So I circled it so I know I need to add it on at the end. And then the square root of x squared, that's just x. That's going to happen 3 more times. So I have 4 x's total out in front. And then this is where my remainder comes into play. Since it wasn't a nice square root, I just leave it inside the square root sign, add it on at the end. Clean this up a little bit. Well, I have 4 times 1, 2, 3, 4 x's. So 4 x to the 4th, square root 2. And that would be my simplified expression. So then trying one like part B over here, okay, now we're taking the 4th root, all right, so it's a little bit harder. We got to think more in groups of 4. So just rewriting this a little bit, gotta have my index in there. 16, well, I don't have all the 4th roots off the top of my head, so let's just pull out our calculator so we can kind of see what's going on here. Well, so 1 to the 4th is 1. 2 to the 4th is 16. So 2 is the number we're looking for here. So we have 2 to the 4th. And then looking at the A right here, I have 24 of them, and I want to group them into groups of 4. So 24 divided by 4 is 6. So I could think of this as I'm just going to write it out the long way. I have 6 a to the 4ths. 4, 5, 6. There should be 6 total there. 1, 2, 3, 4, 5, 6. I have 6 a to the 4ths. And then same idea with the B. The only thing is that 13 is not divisible by 4. 4 does not go into 13 evenly. So let's take 1 away. Say that I rewrite this as B to the 12th times B. I still just have 13 B's being multiplied by each other here, but I can divide 12 by 4 to get that I have b to the 4th 3 times, because 12 divided by 4 is 3, and then I just have a b left over. So rewriting this out the long way, like we've done a few times now, this is what it's going to look like. From here, I just move down this list and take the 4th root. Well, the 4th root of 2 to the 4th is just 2. The 4th root of a to the 4th is just going to be a. And I have 1, 2, 3, 4, 5, 6 of those total, so I can use that as my exponent there. 4th root of b to the 4th is just b. And again, I have 1, 2, 3 of those total, so I'll put that 3 as my exponent. And I can't take the 4th root of just a b, so there's my leftover. So I leave it as the 4th root, and I leave the b inside the radical sign, and there we go. That is our simplified answer. So why don't you guys go ahead and pause the video and try these guided practice questions on your own. Come back when you're ready for the answer. Okay, simplifying 1a here. A perfect square that goes into 12 evenly is going to be 4. So I have 4 times 3. And then square root, so I'm thinking 2s, I'm thinking pairs. We'll see the 6, c divided by 2 is 3, or 6 divided by 2 is 3. So I have 3c squareds, right? Because 2, 4, 6. I have 6 altogether, just broke it down into pairs. And then d cubed, well, breaking that down into pairs, this can be d squared times d, which is kind of what I needed. So I'm just going to rewrite that inside my radical sign. And then I'll clean it up a little bit. Square root of 4 is 2. Square root of 3 is not a nice number, so I'm going to circle it so I know it's part of my remainder at the end, part of what's left over. Square root of c squared is c. I have 1, 2, 3 of them, so I'll make the 3 my exponent. Square root of d squared is just d. And I just have 1 of those, so I just need to leave it as d. Square root of d is not a nice number. It's not a group of 2, so that's also part of my leftover. That goes inside the square root sign. And there's my simplified answer. So then our last little guided practice one here, we're working with our cubed root, so we're thinking groups of 3. Breaking this down, 27 is actually 3 cubed. And then 12 divided by 3 is 4. So I actually have 4 y cubes here. I'm just going to go ahead and write them all out. And then 7 divided by 3 is not a nice number, so I'm going to rewrite this as z to the 6 times z. 6 divided by 3 is 2, so I have 2 z cubes with 1 z left over. So then my last little step here is to clean this up. Oops, I don't need that yet. Well, actually, yeah, I don't need that yet. The cubed root of 3 cubed is 3. Cubed root of y cubed is y, and I have 1, 2, 3, 4 of those, so I use the 4 as the exponent. The cubed root of z cubed is z. I have 2 of those, so that 2 goes as my exponent. Can't take the cube root of just a single z there because I'm looking for groups of 3, so I leave that alone. Oops, I don't know why I wrote 3 again. That should be a z. And that would be our final answer. Our simplified answer, I should say. And that's kind of using that product property. In the scheme of things, we're still just simplifying like we did in section 6.4, but now we just have something left over inside our radical sign. So then moving forward, we talked about multiplying, so now let's kind of talk about dividing. Just a little refresher. So if we are taking the square root of a fraction or the nth root of a fraction, it's the same as just splitting up the square root on the numerator and the denominator. So if we take a look at this example right here, say we're taking the cubed root of x to the 6 over 8. That's the same as just taking the cubed root of x to the 6 on the top and then the cubed root of 8 on the bottom, which help us simplify in the end. So we're going to use that.
sorry. I don't know that. But I do have a skill you might
Alexa, quit listening. Thanks. My bad. Alexa's worse than Siri sometimes. Okay, so we're going to use that to help us split up square roots when we're given a fraction. So before we try an example, there is something that we need to touch on. Let me get it up into the view. Okay, something that we're going to have to do is we're going to have to rationalize a denominator. We don't like square roots in the denominator. All right, just like we can't have a 0 in the denominator, we don't like negative signs inside the radical. We don't like having square roots in the denominator. So to rationalize it, if it's just the square root of a number, if it's a square root, we're going to multiply the top and the bottom by that square root in order to get a whole number in our denominator. When we have an nth root, so a cubed root, a fourth root, a fifth root, it gets a little messier. And say we're looking at our example over here, we have 5 divided by the cubed root of 2. To get rid of that, we're going to multiply the top and the bottom by the cubed root of whatever the inside is to the power, that's the index minus 1. So that's where we got this 2. And then we multiply so that our goal is to get a whole number on the bottom. That's always our end-all goal. We will do an example like this, so don't worry if this part was confusing. We will do an example like this in a second. So let's go ahead and jump to those. Example 2, simplify expressions with the quotient property. So the first thing we want to do, as we're looking at part A here, is we want to split this up so that we have a square root on the top and a square root on the bottom. So this is going to look like x to the 6th, square root of x to the 6th, over the square root of y to the 7th. From here, before even think about rationalizing it, I want to go ahead and simplify these as much as I can. It's just going to make my life a lot easier at the end. So we're just going to think about, okay, square root of x to the 6th, I'm thinking pairs. So this is going to be x squared times x squared times x squared, because I have 6 divided by 2 is 3, so I have 3x squareds there. And then kind of the same idea down here. I can't divide 7 by 2, but I can rewrite this as y to the 6th times y. And then again, 6 divided by 2 is 3, so I have y squared, y squared, y squared, with 1 left over, y. So then bringing this down to clean it up, the square root of x squared is just x. And I have 3 of those. So it's just x cubed in the numerator. We lose the square root. Down here, the square root of y squared is y. And I have 3 of those. And I have 1 left over, so I do have to keep the square root in the denominator. And now I can rationalize it. All right, so to rationalize this, since it's just the square root of y, we don't have an index greater than 2, I'm going to multiply the top and the bottom by the square root of y. And the reason I'm allowed to do this is because this is technically just multiplying by 1, right? 4 over 4 is 1, 5 over 5 is 1, square root of 5 over the square root of 5 is 1, so it doesn't actually change our problem. But by doing this, I get rid of the square root in the bottom. Let's see how that happens. When I multiply like this, I just multiply straight across. X cubed times the square root of y. Just looks like that. On the bottom down here, again, I still just multiply straight across. Y cubed times the square root of y times the square root of y changes to y cubed times, well, the square root of y squared, right? I have 2 of them, so it's square root of y squared. Well, we know that these are inverses of each other, so we know they're going to end up canceling each other out. And this is going to leave us with x cubed square root y over y cubed. Well, this is just going to end up being y. And our last little bit here to simplify, y cubed times y. We know that's an invisible 1 there. We add our exponents to get y to the 4th. And that would be our simplified answer with a rationalized denominator. Lots of words, but it's just a process in math you have to know how to do. And we actually kind of have done something like this when we went over imaginary numbers. So we have seen something like this before, but it's good to review. Ones like part B over here, though, get a little bit harder, and this is that harder example I was talking about. So again, the first thing I want to do is I want to split up our fraction here. So this is really just the 4th root of 6 on the top here. On the bottom, we have the 4th root of 5x. And since our index is bigger than 2, this is where we have to change the bottom up a little bit in order to get it to cancel. So basically, we're going to take each part of this radicand right here in the denominator, and we are going to raise it to an exponent 1 less than our index. So our numerator over here doesn't change. We still have the 4th root of 6. That doesn't change. Whoops, actually, I lied. We're multiplying now. Just have to multiply first before I can simplify here. Let's try this again. Gotta multiply the top and the bottom by the same thing in order to get this to work. So I want to multiply the top and the bottom by the 4th root of 5 to the 3rd power times x to the 3rd power. I got 3 because I knew I needed to subtract 1 from the index. So let me move this so you guys can see it a little bit better. Maybe. Okay. And then I'm going to multiply the bottom by the same thing as well. So then when I do this, again, since they have the same index, I can multiply the insides together. So up here, in my numerator, I'm going to have the 4th root of, well, 6 times 5 cubed times x cubed over down here, I'm going to have the 4th root of 5x times 5 cubed x cubed. And then I can clean this up a little bit. 6 times 5 cubed, I don't know that off the top of my head. I'm sure you guys don't either. So I can type it into my calculator here and do 6 times 5 cubed to get 750. So I have the 4th root of 750 times x cubed. It's actually going to end up staying like that for a while. And down here, I still have the 4th root of, well, I'm going to break this down a little weird to get my groups of 4. I have 5 raised to the 1st power times 5 raised to the 3rd power. Since the bases are the same, I can add the exponents and get 5 to the 4th. And then since I have x to the 1st power times x to the 3rd power, again, I can add, since the bases are the same, I can add the exponents to have x to the 4th. So then to wrap this up here, the top stays the same. We still have the 4th root of 750 x cubed over, well, the 4th root of 5 to the 4th is just 5, and the 4th root of x to the 4th is just x, and this is what my answer would be after I've rationalized the denominator. Again, I know it's kind of a lot of work, but it's something we have to go over. We're not going to have a ton of these like this, but you need to know how to do them, and that's how. Remember that you're always going to just raise everything inside the square root to 1 less of the index. And your end all goal is to get no square root down here at the bottom, no radicals in your denominator. That's a no. We don't want that. So go ahead and pause the video and try just 2a on your own. You don't need to do 2b. Try just 2a on your own. This is back to 1 like the first example, and come back when you're ready to check your answer. Okay, so the first thing you want to do is simplify the numerator and the denominator. Since we're taking the square roots, I'm thinking of pairs, groups of 2. Can't divide 9 by 2 evenly, but if I break this down to a to the 8th times a, 8 divided by 2 is 4. So I have 4a squareds up here. And then 1a left over, right, because there's that 9a's, and then down here in the denominator, again, I can't divide 5 by 2, but if I do b to the 4th times b, 4 divided by 2 is 2, so I have 2b squareds, 1b left over. Cleaning this up a little bit, all right, square root of a squared is just a, and I have 1, 2, 3, 4 of those with the square root of a left over. And then down here, I have square root of b squared is just b. I have 2 of those with the square root of b left over. And now all that's left is to rationalize my denominator. In this case, I just want to multiply the both by square root of b, top and bottom, multiply across the top here. I get a to the 4th, and since they're both the square root, I can do square root of a times b, multiply them together. And down here, I got b squared. And then square root of b times the square root of b is like the square root of b squared. Cleaning up my denominator here, this a to the 4th square root of ab is not going to change. Square root of b squared is just b, so I have b squared times b, which, just like it did in the example earlier, is just b cubed. You guys can add those exponents together to get b cubed, and that would be my simplified answer for that one. So I know I've thrown a lot of rules at you when we've been doing stuff with radicals here and nth roots, but here's a nice list that probably would help if you guys got written down in your notes of all. It's like a summary of all these rules we've been talking about. The multiplying rules, the when you need to rationalize what you can and can't have. So if you guys want to go ahead and pause this video so you can get the summary written down in your notes somewhere, it's going to be a nice list to be able to look back at. Okay, and then moving on to example 3. Now let's talk about multiplying radicals. And basically our rules here are we can multiply together what's out in front, and then as long as it has the same index, we can also multiply what's on the inside. So what this is going to look like is if I multiply what's in front, I have 5 times 3. Then all underneath this cubed root here, I'm going to have negative 12 a b to the 4th times 18 a squared b squared. And we can go ahead and clean that up a little bit. 5 times 3 is 15. Negative 12 times 18, I can bust out my calculator here. Negative 12 times 18 is negative 216. This is still all underneath that cubed root. We have negative 216 a to the 1st power times a squared. We add those exponents to get a cubed. B to the 4th times b squared. We add our exponents to get b to the 6th. Now I can simplify this a little bit. We have the cubed root here of negative 216. I just have a gut feeling that this might be a perfect cubed. I don't know off the top of my head, but I'm going to go ahead and check. So I'm going to go to my math button, pull up my cubed root, type in negative 216, and it is. It's negative 6. So this is going to be negative 6 cubed. Well, a cube's already in my group of 3, so that's good. And then breaking down this b to the 6, well, 6 divided by 3 is 2. So I have 2 b cubes. So then cleaning this up a little bit, I have 15. Cubed root of negative 6 cubed is going to be negative 6. Cubed root of a cubed is a. Cubed root of b cubed is b, and I have 2 of those to get a b squared. And last but not least, oops, can't see it, 15 times negative 6 is negative 90 a b squared. And that's an example of multiplying two square roots. Again, you can multiply the outsides together, and as long as the index is the same, as long as they both have the same number inside the little check mark thing, you can multiply the insides as well. A big rule to remember is that when we're multiplying variables, we add exponents. Exponent rules have not gone away, so those are going to help here. So then moving on, we talked a lot about multiplying radicals, so now let's talk about adding and subtracting radicals here. Let me bring it into focus. There we go. Just like when we were adding and subtracting monomials, we thought combine like terms. Adding and subtracting were the easy ones. We just had to combine like terms. Well, same here, but instead of like terms, we think like radical expressions. So looking at some examples, we're looking for the index. That's how we know if they're like radical expressions, because we're looking for the index. And since this is both the square root of 3b and 4 times the square root of 3b, they both have the same index, so they are like radical expressions. Over here, we have 3b and the cubed root of 3b. They're unlike, so even though the radicand is the same, our indexes are different, so we can't add them. I forgot to point that out. To add and subtract, the insides have to be the same as well. Forgot to add that here. The index has to be the same and the radicand has to be the same. This one, even though the radicand's the same, our index is different. That's why they're unlike. And over here, even though the index is the same, our radicand's different. So to add or subtract, the index and the inside must be the same. All right, so then let's do an example down here. Example 4. Simplify this. First thing we're going to do, let's go ahead and simplify our square roots to see if we get any like radical expressions. So breaking down this 98, I don't know all the factors of 98 off the top of my head, so let's go through a little guess and check here. 98 is a pretty big number, so I'm just going to kind of go with it. So let's do 98 divided by 4, 24.5, no go. Maybe 98 divided by 16, that's a no-go. 98 divided by 36 maybe, still a no-go. So let's try 7 squared, 98 divided by 49. There we go, 49 and 2. So this is just going to be the square root of 49 times 2 minus 2 times, well, we're back to that 32. We've seen that a lot in this last 2 sections. That's going to be 16 times 2. Simplifying some more, the square root of 49 is 7. 2 gets left behind. Minus 2 times the square root of 16 is 8. And again, 2 gets left behind. So cleaning this up, I have 7 square root 2 minus, square root of 16 is 4, not 8. I am off my A game today. This should be a 4. To get that this is minus 8 times the square root of 2. Basically now I just treat the square root of 2 like it was an x, and I would do 7 minus 8 is going to give me negative 1 square root 2. So when you get to this point right here, treat what's in the square root, what's in the radical sign, like a variable, and then just subtract the coefficients to get negative square root 2. And we're good to go here because these are both square roots and the insides both matched. So why don't you guys go ahead and pause the video and try these two on your own. More adding and subtracting, but try these guys on your own. And we're almost done, I promise. Okay, first thing I gotta do is break down these square roots here and simplify them a little bit to see if I have any like radical terms. 8 is gonna be 4 times 2 plus 3. 50 is 25 times 2. Okay, so I have 4 out here in the front. Square root of 4 is 2. Square root of 2 gets to stay behind. Plus 3, square root of 25 is 5. Square root of 2 stays behind. Clean this up a little bit. 4 times 2 is 8 times the square root of 2 plus 3 times 5 is 15. With the square root of 2 there. And then I have 8 plus 15 to give me 23 square root 2. And that's how we would have handled that one. And then 4b gets a little bit trickier. Again, still just breaking down the square root first. We have 5 times, well, 12 is 4 times 3, plus 2 times 27 is going to be 9 times 3. And then square root of 128 has a little bit more guessing and checking going on. So I'm going to bust out my calculator here. Or you can do it in your head if you think. 128, I'm going to try some bigger ones first. 128 divided by 36. Not a nice number. 128 divided by 49. That's a no-go. 128 divided by 64. There we go. 64 and 2. Okay, cleaning this up a little bit. got 5 out in front. Square root of 4 is 2. 5 times, leave the square root of 3 alone. Cleaning this middle part up a little bit. 2 stays out in front. Square root of 9 is 3. Leave the extra 3 alone inside the square root sign. And then cleaning up this last part, square root of 64 is 8. 2 stays inside the radical sign. This changes to 10 square root 3 plus 6 square root 3 minus 8 square root 2. Gotta see what I combined. Well, the only terms I have here are this square root 3. So I have 10 plus 6, 16 square root 3 minus 8 square root 2. And that's how we would go about adding and subtracting like radical terms. Doesn't get much harder than that. It's usually the gist of it. You just have to break them down first to see if there's any like terms. And then once you get it down to the basic simplified square roots, treat it like it's a variable and add from there. A few more things to go over in this section, then we'll wrap it up. We can also multiply radical expressions like this. And just as if this was an x and a y rather than square roots, we would FOIL. We're going to FOIL here. So remember, FOIL's first, outside, inside, last. So if I multiply my first here, I have 4 times 3 is 12. Square root of 3 times the square root of 2 is going to be the square root of 6. Remember, we just multiply the insides together. My outsides here in purple, 4 times negative 6 is negative 24 times the square root of 3. Still have nothing to combine with that, so it just stays attached there. Insides, 5 times 3 is 15. 2 times 2 is 4, so I have the square root of 4. And my last, 5 times negative 6 is minus 30. Square root of 2 stays there at the end. So clean this up a little bit. We have 12 square root 6 minus 24 square root 3. The square root of 4 is 2, so this is just 15 times 2 minus 30 radical 2 to get the final answer of 12 square root 6 minus 24 square root 3 plus 30 minus 30 radical 2. I'm not worried about per se the order it's in, like standard order or anything like that, standard form. You just gotta FOIL and make sure you get all parts. Chances are at least one term is gonna simplify like this guy did right here. So then last but not least, last example here, dividing, more dividing. We've talked a lot about everything, more dividing. Whenever we have a radical expression in the bottom that looks something like this, we're going to use the conjugate to rationalize the denominator. This is what we use with imaginary numbers, where we just multiply. Instead of having a minus 1 here, we're going to multiply the top and the bottom by the square root of 5 plus 1. So basically, I'm going to multiply this guy. I'm going to use rationalizing it, so I got to use the denominator here because I don't want this square root in the denominator, by square root of 5 plus 1 on the top and the square root of 5 plus 1 on the bottom. I like to put parentheses around it because it helps me remember, oh, I need to distribute this 2 to both of these to get 2 square root of 5 plus 2 over, and this is where I'm going to have to FOIL. So my first square root of 5 times the square root of 5 is going to be the square root of 5 squared. Square root of 5 times 1 is plus square root of 5. Negative 1 times the square root of 5 is minus square root 5. Negative 1 times 1 is minus 1. Multiplying by the conjugate helps us here because this part right here should always cancel each other out. Positive square root of 5 minus square root of 5 is just 0. That part should always cancel each other out. So we're left with 2 square root 5 plus 2 in our numerator, while square root of 5 squared is just 5. If that part cancels each other out, minus 1, we have 2 square root 5 plus 2 over 4. The last little bit we have to do here is simplify because 2 divided by 4 is 1/2, 2 divided by 4 is 1/2, so this is actually square root of 5 plus 1 over 2. And that would be our simplified answer. Kind of a lot, but the rules that we went over today haven't changed. A lot of it's been reviewed. We just kind of put it all together in one lesson into a lot of examples. So here's your homework for this section, page 419, 1 through 15 odds. It will be posted on Classroom with homework pages, and email me if you have any questions.